Hi friends, welcome to follow up. Let's have a look at problem 2792, count nodes that are great enough. This is a newly appeared problem. So in this video, we're going to explain a solution based on recursion. So basically, we're going to use a coding style similar to the previous video, that is the video for problem 2791. So here we do not pursue the best term complexity. Basically, we want to explain the problem logic. So here we are given a root to a binary tree and an integer key. A node of this tree is called great enough if the following hold. First, each subtree has at least key nodes, and its value is greater than the value of at least key nodes in its subtree. So this defines what's a great enough node. So we are required to find the total number of nodes in this tree that are great enough. So here the node U is in the subtree of node V if U equals to V, or V is an ancestor of U, right? In other words, when doing the counting, we want to count all the offsprings and itself. So here are three examples. So in the first example, so for example, the k equals 2. For 7, so 7 for sure is greater than 1 and 2, right? 7 counts. So we see 6 is greater than 3 and 4, so 6 counts. So similarly here, 5 counts, but all the leaf nodes do not count. So we're going to get 3. So here for example 2, so because the leaf nodes have larger values than the root, so this problem, so we're going to return 0, right? For example 3, so here we have root is 3 and the two leaves have values 2, so we are going to count this root node as good enough, so we get 1. So the additional assumptions are the following. First, the number of nodes in the tree is given by the closed interval 1 to 10 to the power 4, right? So 10 to the power 4 is a decent large number. And secondly, the node values are in between 1 and 10 to the power 4. And the key is in between 1 and 10, right? So basically, this problem logic is very straightforward. So here, in order to quickly solve this problem, we first ignore the term complexity. In other words, we ignore optimizations. So later, maybe you can try to do some extensions using merge sort, or using segment tree, or using heap data structure. So here we just use plain sort. So I'm going to write two versions of the solution. So the second version will be a slight optimization we may see, or just more practice. So first, I'm going to initialize a result variable. So this is the counting variable, right? So we are going to make this result non-local when we write a inner function. So this way, we are going to automatically update this variable. Or if you like, you can use this. You can use a field, let's see, self result equals 0. So this way, you can continuously update this one, right? Let's first content ourselves to doing this, and then we can comment on this version, on this use of the attribute or field. So now let's do the depth first search. So going to from the root. So basically we are going to do a traversal, right? So first, if not a root, so we're going to return an empty list. So this is very standard. So let's do not forget non-local result. So the reason we want to make this a variable non-local is to continuous update the counting variable result, right? So we make this non-local. Then this is one stop condition or base case, and then basically we can do the traversal for left subtree and the right subtree. So this is actually rather straightforward. Let's introduce an intermediate variable. So basically we want to do DFS root left, and then we do addition. So this addition is a concatenation of two lists. So root right. So this contains all the offsprings of the current root, right? Basically, we want to check if within this array there are at least k nodes, and also there are at least k nodes with values less than the root value. So we can do a sort. Let's do a sort in place from small to large. And then we want to check if length of this array is greater than or equal to k, right? So in other words, we have at least k elements. And then we want to make sure the first k element will be larger than the root value, smaller than the root value. So we just need to check k minus 1. So this at this node, right? If this value is less than the root value, then all the values from index 0 to up to index k minus 1 will be less than this value, right? And then in this case, we're going to count the current root node as a great enough node. So we're going to increment this variable by 1, right? And then basically what we want to return is nothing but the array plus, say, the root value, right? And so basically this is a traversal. Here we first traverse the left and then right, and then add the root value. So this corresponds to post-order traversal. Actually, you can add this root value in front. It's corresponding to pre-order traversal, right? But you cannot add in between because after you do sort, you cannot distinguish if this is the root value itself, right? So then what we want to do is to, after we write this utility function, we want to call this function, right? After we call this function, so this result variable will be automatically updated. Then we are going to return this result state. So this is the problem logic. So now, before we make any comments, let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So now let's quickly comment on the use of the field in the coding. So let's copy this part, and then I'm going to change this one to be version v1, right? So here, actually, we can just delete this result variable, and then we introduce a field. And so here we do not need this non-local variable, right? So then what we are going to do here, so we have this, we just self result incremented by 1, right? Then we still return this one. So we just return self result. So this is another solution format, which is the same as the first version. Now let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So with this one, let's introduce another version. Let me copy this one, this first version. So what I'm going to do here is I'm going to change this one to be version v2. And now let's focus on this version. So here actually we can do something more. For example, here we do a sort, and then we add this one, and then we do a sort again. So this is not this is cool. This is okay, but let's maybe do something like this. So we can from bisect we can import the insert function. So basically, it will insert an element to make it still maintain the list or iterable sorted. So here, what we want to do is after we do the sort, and then we increment this one. And then what I'm going to do here first is to insert this one. So insert. So I'm going to this one. I'm going to insert this root value. So this way, the array will be in a sorted state. So let's return this array. So let's do a test for this version. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So for now, actually, this solution, basically, we do this problem in a very straightforward way or verbose way. We didn't pay attention to the term complexity. So actually, if we want to further elaborate on this problem, you can try merge sort. So, and like here, merge these two, or you can do segment tree. So this it will improve term complexity, or you can use heap. Yeah. So basically, with that said, we will encourage you to try these extensions or try to write the solution in different formats to deepen your understanding about this problem or coding format. So with that said, basically that's about it for this video. Thank you.